Art of factorization. This is an IMC 2019 problem, right? Which is actually an infinite product. But over here, this product tends to be a telescoping product, right? And to know how it telescopes, how it cancels, we need to have a good idea on factorization. So that's what we are gonna discuss today, right? Numerator is straightforward, but for denominator, you have to make quite a few, like a lot of factorizations. Let's see how we do that. So this is a product from n equals to 3 to infinity, right? Numerator, you can just take n common, right? And then because there's a square, you will have n square, and then n square plus 3 whole square, right? Over here in denominator, you actually have two options to factorize. You can either do it like n square cube minus 4 cube, right? Or you can also do like n cube square minus 8 square, right? But in numerator, there's this 2 degree and 4 degree expressions, right? So to have similar expression, we'll use this first one. So, okay, n square cube minus 4 cube. This gives us product from n equals to 3 to infinity, n square plus 3 whole square by, this is n square minus 4, n to the power 4 plus, this is 4n square plus 16, right? Okay, now, now I can actually break this into two different products, right? N square by n square minus 4, and then n square plus 3 whole square. Because like these are 2 degree expressions, and these are 4 degree expressions. And infinity, this is just going to 1, right? And this is just going to 1. So it makes sense that both of them will have values, right? Okay. Now, to further, I will just deal with them one by one, right? Okay, now the first product, if I try to factorize it even more, I have n by n minus 2, n plus 2, right? Now you can actually see that in this product, except for the first two terms generated from this n by n minus 2, all the others are gonna cancel with this one, right? Because after 2, this becomes n plus 2 by n, which cancels with this term that is generated 2 steps ahead. I mean, 2 steps previously, right? So you can actually see that this is gonna be like 3 times 4 by 1 times 2, right? Yeah, but let's do it rigorously, because like sometimes, let's say if you feel that from this n equals 3 to infinity and the n minus 2, then you might feel that like after two terms, like whatever this gives cancels with this from the two terms previous, right? And then you might just think that this is gonna be something like 1 over 1 times 2, but that's not the case. That's not the case actually, because if you let's say do it like this, limit n goes to infinity, the product from n equals to 3 to n, right? Now what you will get is this is gonna be uh n minus 1, right, by 3 minus 2 is 1 2. So, and this is gonna go into infinity. So you cannot just base your intuition to always work. Therefore we have to go towards rigor, right? So let me just do it rigorously. So what I'm gonna do is I'm gonna substitute these limits by capital N and let limit n go to infinity. Limit capital N go to infinity, or and over here. Okay, now we are gonna do this. Okay, now also let me break these two products into like two different products, right? Limit n go to infinity, limit n go to infinity, right? And then this becomes n by n minus 2, then this is n by n plus 2, right? Okay, so now we can see them as two different products, right? We can actually see them as two different products. I can also have product over here from n equals to 3 to n, and n is going to infinity. Now first one, okay, since this is n by n minus 2, like every term 2 step afterwards, right, over in n minus 2 is gonna cancel with the term 2 step for like previous, right? So this is just gonna be n minus 1, right, and that's gonna be cancelled with 3 minus 2. Yeah, 3 minus 2 and 4 minus 2, right? Because okay, wait, yeah, because this product is just going to be 3 by 1, 4 by 2, 5 by 3, up to n by n minus 2, right? So all these gonna cancel out, right? All these gonna cancel out. So you are just left with n minus 1 by 1 and 2, right? So that's what I have over there. And then next one is also similar, right? So what you're gonna have is over here numerator where you will have 3 and 4, and denominator you will have uh okay you will have, when there's n minus 1, n plus 1 and n plus 2, right? Because over here this only goes up to n, so the last two terms n plus 1 n plus 2 will be extra and they will just remain over there. Okay, so now after this you will have limit capital N goes to infinity, 3 times 4 by 1 times 2, and then n minus 1 by n plus 1 n plus 2, right? And then I think it's easy to take that limit now. This is now just 6. And then to take this limit, you can actually divide numerator by n square. That gives you 1 by 1 minus 1 by n. And then 1 plus 1 by n, 1 plus 2 by n, right? And when n goes to infinity, this just becomes 1, 1 minus 0, 1 plus 0, 1 plus 0, right? And that just becomes 6. So that was the first part. Now for the second part, again, okay, this one it's a really good factorization thing. So what you're gonna do is you will be trying to factorize the denominator, right? But if you do it like n to the power 4 plus 4n square plus 4 plus 12. So if you're gonna complete this square, this one over here is not perfect square, and then you are stuck with it. So what you should be doing is actually take the first and the last thing, n to the power 4 and 16, and then try to complete that square. N to the power 4 plus 8n square plus 16 and minus 4n square. In this way, this is a square, this is a square, and again you can make some more manipulations. So yeah, that's what I'm gonna do. So yeah, we have limit n goes to infinity over here as well, right? And then product from n equals to 3 to infinity, n square plus 3 square by n to the power 4 plus 8n square plus 16 minus 4n square. Okay. After that, we have limit capital N goes to infinity. Product from n equals to 3, actually capital N, 3 to capital N, 3 to capital N. Now this becomes n square plus 3 square by, now this becomes n square plus 4 whole square minus 2n whole square, right? And then you can write that as limit n goes to infinity. Product from n equals to 3 to n of n square plus 3 square by, now this one will be n square minus 2n plus 4, n square plus 2n plus 4. Now, if you try to complete the square for the n square minus 2n and n square plus 2n, now you will notice something really beautiful. Thing is, now if you try to complete those squares, this is n square plus 3, n square plus 3, right? The first one becomes n minus 1 square plus 3, and this one again becomes n plus 1 square plus 3. Now again you have the telescoping thing over here, because now if you try to write this as two different products, right? The first product from n equals to 3 to n of n square plus 3 by n minus 1 square plus 3. The second one as n square plus 3 by n plus, okay, wait, let me write it as capital N. Capital N. N plus 1 square plus 3. Now what you're gonna have is, in the first one again, first one, this denominator, like every next term in denominator is gonna cancel the every previous term, right? So that's why what you will just have is limit capital N goes to infinity. This capital N square plus 3, and in denominator, the 3 minus 1 square plus 3, right? The first term won't get cancelled, and in numerator, last term won't get cancelled. Similarly over here also, okay, in numerator, like first term will remain, and in denominator, last term will remain, right? So you have this. So that means you have 3 square 9 plus 3 12 by 2 square plus 3 7. And limit n goes to infinity, n square plus 3 by n plus 1 square plus 3, right? Now if you try to divide both numerator and denominator by n square, what you would have is limit n goes to infinity, 1 plus 3 by n square, right? And then over here also you will have um 1 plus 1 by n square plus 3 by n square, right? And then now if you take the limit, this is 12 over 7 times 1 plus 0 by 1 plus 0 square plus 0, right? And that's just 1. So it's 12 over 7. So now actually to break the product like this, we need to be sure that both to break the limits like this into two products, we need to actually make sure that both of these should exist, right? And they actually do, even though we didn't know at the beginning, both of them actually exist. So then it's fine to break them, right? Now, so therefore, this whole thing is gonna be what 12 over 7 into 6. Sorry, 12 over 7. 12 over 7 into 6, which is 72 over 7, and that's the answer. So over here, actually the interesting part is how you factorize this expression, right? Like how you choose to factorize that, because our solution like entirely dependent on that. Because if you couldn't factorize it like this, then there's no way you could have made this progress, right? So yeah, sometimes it's necessary and helpful. Also over here, like how you factorize this expression. Sometimes it's like important about knowing how to factorize certain expression, because there can be multiple ways to do it, and only one of them will lead you to a right path, right? So that was the moral of the story. And after that, also, like don't just blindly cancel and write terms, because actually you should try to be rigorous, right? Otherwise, like your intuition might lead you to wrong destination, wrong result sometimes. And yeah, with that and the good limits, we have the answer. So that was it, guys. Hope you enjoyed the video. Hope you learned something about factorization, about being rigor, and like all these things. And hope you apply it to your problem solving as well. And I look forward to seeing you in the upcoming videos too.